Areas and lengths in polar coordinates. You'll hopefully recall from either geometry or trigonometry course that the area of a circular sector is defined as area is equal to 1/2 r squared theta. It can be shown, and there's a proof in the textbook, that the area of a polar region is defined as the integral from a to b of 1/2 r squared d theta, where the a and b are, in a sense, angles at the beginning and the end of the polar region, and r is a function of theta. So for example, let's say we were asked to find the area that is bounded by r is equal to e to the theta over 2 from pi to 2 pi. Now if you were to sketch this curve, r is equal to theta over 2, that's called a spiral. It ends up being a spiral. And so if theta was 0, we'd have what, e to the 1/2, e to the 0, which is 1, so let's just say that be this point. And then if r was pi, we would have e to the pi over 2, which is about 4.8. 1, 2, 3, 4.8, so that's about here. And we get a curve that's something like this. And then finally, if r is 2 pi, we would have e to the pi, which is 23, roughly. So, and it jumps, it continues to increase, and it's way out here somewhere. So what we're talking about, this region that we're talking about, is this shaded region right here. And the area of that shaded region can be defined as the integral from pi to 2 pi of 1/2 of r squared d theta. And in this case, the r is e to the theta over 2. We can immediately bring that 1/2 outside the integral. And we have the integral from pi to 2 pi. And e to the theta over 2 squared would be e to the theta d theta. And the antiderivative of e to the theta is e to the theta. So that would be 1/2. And we'd have e to the theta from pi to 2 pi. And so then the area would be 1/2 of e to the 2 pi minus e to the pi. And we could approximate that area if we want. Find the area that is enclosed by r equals 2 minus sine theta. Alright, so what I'm going to do here is sketch the curve first so I can get an understanding. See, they didn't tell us here the starting and stopping points. We have to figure that out on our own. And so we need to find how long it takes to enclose this figure. So I'll start, like I did in the previous section, by drawing a Cartesian graph of y equals 2 minus sine x. Alright, so 1, 2 minus sine x. So since it's a sine curve, it starts, it'll have a period of 2 pi, and the amplitude is 1. So let's see, it'll start at 2, end at 2. At the halfway point, it's at 2. And since it's a minus, it's going to decrease first. And so here is the Cartesian graph. And now transferring that over to polar ideas, I'll make this, there's a radius of 2. So we have the point 2, 0. And let's see, then the radius decreases to 1 at pi over 2. And then increases back to 2 at pi. It continues to increase to 3 at 3 pi over 2, and then it's back to 2. So we get a curve that does something like this. It's not exactly circular. In fact, it's not a circle. But notice that I completed the curve from 0 to 2 pi. So what that tells me is, when I set up my integral, I will integrate from 0 to 2 pi of 1/2 r squared d theta. Again, I can bring the 1/2 out. Integral 0 to 2 pi. And let's see, I'll multiply that out. That's 4 minus 4 sine theta plus sine square theta d theta. All right, and remember what we learned back in an earlier section, that if we're going to integrate this sine square theta, we use an identity and replace that with 1/2 of 1 minus cosine 2 theta. All right. I think that was in the section on trigonometric integrals. All right, so we've got a 1/2, and now we can find all these antiderivatives. So I'd have a 4 theta. The antiderivative of 4 sine theta would be plus 4 cosine theta. And let's see, we'd have a 1/2 times 1, the antiderivative of 1/2, that's a 1/2 theta. And the antiderivative of 1/2 cosine 2 theta, that would end up being, well, we'd have to use a u substitution there. Let u equal 2 theta, and we'd end up with 1/4 sine 2 theta. And we have to evaluate all this from 0 to 2 pi. So I'd have a 1/2. Now substituting the 2 pi. Let's see, I'd have 4 times 2 pi, that's 8 pi. 4 times the cosine of 2 pi. The cosine of 2 pi is 1, so that's a plus 4. Plus 1/2 of 2 pi, so that would be another pi. Minus 1/4 of sine of 2 theta. All right, so if theta is 2 pi, then sine of 2 theta is sine of 4 pi, and the sine of 4 pi is 0, and 1/4 of 0 is 0. All right, and subtracting, now substituting 0. 4 times 0 is 0. 4 times the cosine of 0. The cosine of 0 is 1, so that's a plus 4. 1/2 of 0 is 0. Sine of 0 is 0, so that's a minus 0 here. Lots of zeros there. And so if we simplify this, we'd have 1/2 of 8 pi plus pi is 9 pi. We've got a plus 4 and a minus 4, so 1/2 of 9 pi. And so that's 9 pi over 2. All right, and so the area enclosed is 9 pi over 2 square units. Find the area that is enclosed by one loop of r equals 5 sine 3 theta. All right, like in the previous exercise, I'm going to start by thinking of the Cartesian graph. R sine 3 theta, 5 sine 3 theta, so 5 sine 3x will have an amplitude of 5. And its period is going to be 2 pi over 3. So if this is 2 pi, I'm going to split it into thirds. There's 2 pi over 3. It completes a full cycle in that amount of time. All right, and so since it's a positive 5, it'll increase first and then decrease. And so what we get is this, and it repeats over and over and over again. All right, so again, now thinking of this in terms of r and theta, and I'll make this 5. There's my maximum of 5. So, curve starts at 0, and let's see, if that's 2 pi over 3, then this is pi over 3, making this pi over 6. So we have the point then, the radius is 5 when theta is pi over 6. So the radius increases to pi over 6. And then it goes back to 0 at pi over 3. So pi over 3, right, there's the rate pi over 3. As we get closer, as our angle gets closer to pi over 3, the radius is decreasing and coming back to 0. And then the radius decreases to negative 5, and that would be at, what? That would be at pi over 2. So at pi over 2, the radius is decreased to negative 5. And so if you do a little bit more work here, you'll get a curve that does something like this. Alright, so there's the curve defined by that equation, but we're asked for the area enclosed by one loop. So how about we just focus on that first loop, and notice that that first loop completed right here, completed from 0 to pi over 3. So the area that we're looking for is the integral from 0 to pi over 3, 1/2 5 sine 3 theta square d theta. Alright, so 0 to pi over 3, we've got the 1/2, squaring, that's 25, sine square 3 theta d theta. Let me bring the 25 over 2 out, and we're integrating from 0 to pi over 3. Alright, now we've got that sine square d theta, sine square 3 theta d theta. So again, I'm going to use that substitution. Sine square, remember we saw earlier that sine square theta could be replaced by 1/2 of 1 minus cosine 2 theta. So now instead of a theta, we have a 3 theta. So I can replace this with 25, let's see, we've got 25 over 2, integral 0 to pi over 3. I'd still have a 1/2. Now I'd have a 1 minus cosine 6 theta d theta. Alright, and I can bring that 1/2 out, so I've got 25 over 4. Still from 0, and now taking care of the antiderivatives. The antiderivative of 1 is theta. The antiderivative of cosine 6 theta would be minus 1/6 sine 6 theta. And again, we would evaluate this from 0 to pi over 3. So I've got 25 over 4. Substituting the pi over 3, I'd have pi over 3 minus 1/6 of sine of 6 theta. That would end up being sine of 6 times theta, 6 times pi over 3 is 2 pi. The sine of 2 pi is 0. So pi over 3 minus 0 minus 0 minus, again, we'd end up with a 0 here. So this ends up being 25 over 4 times pi over 3, which is 25 pi over 12. Find the area that lies inside both r equals 1 plus cosine theta and r equals 1 minus sine theta. Alright, so let me again start by sketching these. 1 plus cosine theta has a period of 2 pi, and since it's a plus cosine, it would start at the maximum and end at the maximum, and halfway between would be at the minimum, and then at the other halfway points it would be at the center line. So we would get a curve like that. That's r equals 1 plus cosine theta. And let's see, how about in purple, 1 minus cosine theta would sort of be a mirror image of that. All right, so there's 1 minus cosine theta. All right, so translating that over into polar graphs, let me make, let's see, my maximum is 2, so I'll make that radius 2. All right, so in black, I'll plot 1 plus cosine theta. It starts at the maximum. It starts at 2. And then at, let's see, this is pi, so this is pi over 2. 3 pi over 2, so there's a few nice points. So I've got the point pi over 2, 1, so that would be here. And then it goes to 0 at pi, back out to 1 at 3 pi over 2, and then back out to 2 at 2 pi. So I get a curve that does something like this. All right, and in purple, 1 minus cosine theta starts at 0, increases to 1 at pi over 2, it continues to increase to 2 at pi, and I sort of see the picture here. It's going to do something like that. So the area that lies inside both of these would be this region. So now how to find the area of that region? Well, looking at the symmetry, here's my argument. Considering the symmetry, I'm going to find this area that I've just shaded in orange. I'm going to find that area in orange, and I'm going to multiply it by 4. All right, so that area in orange corresponds to this interval for the purple chord. All right, corresponds to this interval. So the area that I'm looking for would be 4 times the integral from 0 to pi over 2 of 1/2, and I'm working with the purple curve, so that would be 1 minus cosine theta square d theta. All right, and we've done a similar integral not too long ago, so from this point I would just say, okay, now at this point we can use our calculator, and that area ends up being 3 pi over 2 minus 4, which is approximately 0.7123 units. Okay, but the difficulty in this exercise was setting it up. Once we have it set up, then, you know, if you have tools, use the appropriate tools. If we're asked to find the arc length of a polar region or a polar curve, the arc length is defined as the integral from some a to b, beginning to end, of r square plus dr d theta square d theta. And again, this is something that is shown, the proof is shown in your textbook. Find the length of the curve r equals 4 sine theta. Now you might remember this curve. We sketched it in the previous section. R equals 4 sine theta was a circle. I know I drew Cartesian coordinates, but we drew it in polar, and it was this circle with radius equal to 2. And so, well, the length of the curve is just the circumference. And the circumference, recall, is given by 2 pi times the radius. And so that would be 2 pi times 2, and that's 4 pi. So the length of the curve is 4 pi. Now, we know, as we saw in the previous video, we saw that it completed the curve in an angle of pi. So the length of the curve, the arc length, would be defined as the integral from 0 to pi of the square root of r square, so that would be 4 sine theta square, plus dr d theta square. So notice that dr d theta would be 4 cosine theta. So we'd have 4 cosine theta square and then a d theta. Alright, simplifying. Arc length, integral 0 to pi, square root, 16 sine square theta plus 16 cosine square theta, and we've got a d theta on the outside. I can use some factoring here. Integral 0 to pi, square root, 16 by sine square theta plus cosine square theta. And if you remember anything from trigonometry besides the unit circle, you should remember that sine square theta plus cosine square theta is 1. And so then this becomes the integral from 0 to pi of the square root of 16, which is 4 d theta. And so that would end up being 4 theta from 0 to pi. And so that would be 4 pi minus 0, which is 4 pi. And so we've just proven that, the area, that the length of that circle, the arc length of that circle, is in fact the same as the circumference at 4 pi. Now, of course, this was a fairly simple example to show you the technique, and we were able to correlate that with something that we've learned in a simple geometry class. Alright, so now let's see an example that we wouldn't have seen in geometry. Find the length of the curve r equals e to the theta on the interval 0 to 2 pi. Alright, well, they gave us the interval, so we don't have to figure that out. So then the arc length would be the integral from 0 to 2 pi, square root of e to the theta square plus, now notice that if r is e to the theta, then dr d theta would also be e to the theta. And so then we would again have e to the theta square. And we'd have a d theta. So we're integrating from 0 to 2 pi. We'd have a square root of e to the 2 theta plus e to the 2 theta. D theta. And so we'd have the square root of 2e to the 2 theta. So then that's the integral d theta. So 0 to 2 pi, square root of 2, and then the square root of e to the 2 theta would be e to the theta, d theta. We can bring the square root of 2 outside, and the antiderivative of e to the theta is e to the theta from 0 to 2 pi. So I'd have the square root of 2 times e to the 2 pi minus e to the 0, and of course e to the 0 is 1. So the arc length is root 2 times e to the 2 pi minus 1. And this ends up being approximately 755.89. Alright, that concludes this presentation.